We begin by importing the patient's CBCT scan. The software reads multi-slice DICOM files and automatically generates the dataset. Once loaded, patient information can be refined, and AI tools are activated for bone segmentation, nerve pathway identification, and model registration. For this demonstration, we will focus on the maxillary arch and plan a single implant at site number 8. The interface provides 5 primary views: axial, panoramic, cross-sectional, tangential, and 3D reconstruction, each offering a distinct diagnostic advantage. After opening the dataset, the first step is orienting the scan. By adjusting the sagittal, coronal, and axial reference frames, the anatomy is positioned correctly in all planes, ensuring that every subsequent planning step is based on an accurate and consistent orientation. Next, the panoramic curve is refined. As we scroll through the axial slices, the curve is placed centrally along the arch where the roots and cortical boundaries are most clearly visualized. Once accepted, the panoramic reconstruction becomes clearer, more defined, and ready for further analysis. We then import the patient's model scan. The software allows alignment either through manual segmentation or using AI assistance. After selecting the arch, the AI processes the registration. Once the status displays completed, we review all segmentation data, nerve mapping, and the alignment of the scanned dentition before importing the finalized registration into the working dataset. The restorative phase begins with placing a virtual crown for tooth number 8. The crown initially drops into a default position but is refined using both the 3D and cross-sectional views. Proper positioning, incisal height, facial-lingual inclination, and mesiodistal width is essential to define a precise restorative target for implant placement. This forms the foundation for a prosthetically-driven workflow. With the virtual crown established, we proceed to implant planning, where we have the freedom to select from the wide integrated library. Using the axial, cross-sectional, and tangential views, the implant is positioned to respect the restorative axis, bone availability, and mesiodistal safety zones. In the 3D reconstruction, we confirm that the implant emerges through the cingulum, providing a predictable pathway for a screw-retained restoration. The surgical sleeve compatible with a specific guided system is added, and if the sleeve encroaches upon soft tissue, the model is virtually trimmed to remove excess gingival volume, simulating flap reflection and ensuring proper seating of the guide during surgery. This adjusted model becomes the foundation for guide design. Inside the guide design module, the modified model is selected. The path of insertion is adjusted to expose the buccal vestibule and ensure a stable seating trajectory. The software then blocks out undercuts to generate an undercut-free model. Guide extensions are defined by selecting the supporting dentition and adjusting boundary circles to optimize surface coverage and apical support. Offset values, wall thickness, and connector dimensions are set according to printing needs, with large connectors used for additional stability. Inspection windows are added on the buccal and palatal sides, as well as near the bicuspids, providing visibility and adequate handpiece clearance. Finally, engravement markers and labels are applied. Once the guide geometry, sleeve placement, and window positioning are confirmed, the file is ready for export. The workflow concludes with a full 3D inspection of the final guide. Here, the contours, support areas, inspection windows, and sleeve geometry are evaluated comprehensively before fabrication. With the implant position finalized, we move on to designing the screw-retained restoration. For this maxillary central incisor case, the process begins by importing the model scans and the plan, then positioning the planned implant scan body for maximum precision. An emergence profile outline is then drawn around the desired tissue emergence. Given the anatomy of a central incisor, a triangular emergence profile is ideal, enabling a natural and aesthetic transition from the implant platform to the cervical contours of the restoration. Using Exocad software's expert design features, the adjacent central incisor is mirrored to replicate natural symmetry and anatomical proportions. The crown is then placed, its design is adjusted and refined to harmonize with the arch. Next, the custom abutment design is generated, with its morphology automatically guided by the defined emergence profile outline. Then its contour is expertly crafted to essentially promote a healthy, soft tissue biologic width, and have a smooth interface with the overlaying crown design. Finally, the crown design is optimized further, where irregularities are smoothed, contours refined, and slight adjustments are made to length, curvature, and facial profile to ensure that the crown integrates seamlessly with the surrounding dentition. The result is a screw-retained restoration that is anatomically appropriate, functionally aligned, and aesthetically balanced. This completes our full demonstration of the single implant digital workflow, from CBCT import, model alignment, and prosthetically-driven implant planning, to screw-retained crown design and final surgical guide preparation. Thank you for joining us. We look forward to sharing more advanced digital workflows and clinical insights from the team at 3D Diagnostics.